Chapter 3. Examining the principles and the language of Six Sigma. In this chapter, mastering the basic equation of Six Sigma, which is y equals f of x plus... I forget what this little e is. I think it's summation, or e. Little e that looks like a backwards 3. Okay. Recognizing that determinism and variation affect your outputs. Examining the role of measurement in managing processes. Becoming aware of the power of leverage. And balancing risk with precision of outcomes. Like all grand constructions, Six Sigma sits upon a solid foundation. Beneath all the charts, experiments, projects, colored belts, and catchy phrases lie a few fundamental principles that guide and define the whole Six Sigma methodology. In this chapter, you discover the one fundamental equation and 5 basic principles that comprise Six Sigma's foundation. In doing so, you begin to think the Six Sigma way. Starting out with one simple equation, y equals f of x plus e. I'm going to say e until I figure out what it's called. All of Six Sigma can be summarized with what's called the breakthrough equation. One general purpose equation that shouldn't intimidate even the least mathematically inclined. Y equals f of x plus e, where y is the outcome or outcomes or result or results you desire or need. X represents the inputs, factors, or pieces necessary to create the outcomes. You can have several x's. F is the function, the way or process by which the inputs are transformed into the outcome. And E is the presence of error or uncertainty surrounding how accurately the x's are transformed to create the outcome. Figure 3-1 translates the equation into plain English. Read the annotations from 1 to 4. Okay, they start with 1 is x, the independent variables. 2, the f, are transformed by a deterministic function. 3, and combined with random error. 4, to create the resulting dependent variable, which is y. In other words, a set of input variables is transformed by a function or process and combined with error to form the output. The y results from or is a function of the x's. To determine a desired outcome, you apply a transformation process or function, f, on the inputs. You make a loaf of bread by taking flour, yeast, salt, and the other ingredients and transforming them through mixing and baking into a desired outcome. The ingredients and oven settings are the x's, the mixing and the baking are the transformation process function, f, and the resulting yummy loaf of bread is the y. But extra error, e, enters in from the myriad of factors you don't account for, like the local humidity the day you bake the bread, or the freshness of the flour. In the real world, no matter how hard you try, nuisance factors always add extra effect to the outcome. You always experience some degree of uncertainty as to how well your controlled actions produce their desired or expected result. The y equals f of x plus e breakthrough equation is the underlying form of all the statistical tools in Six Sigma, from correlation to curve fitting to design of experiments to hypothesis tests and so on. The interpretation and objective are always the same. What portion of the product or process situation's output, the y, can you attribute to the critical few input factors, the x's, and how much remains in the uncertainty or error, e? The objective is to discover an appropriate level of knowledge regarding the x's and their deterministic effects on y, so that only a tolerable level of e risk remains, error risk. We discuss determinism in the following section. Principle 1, recognizing determinism. If you're like most people in Western society, you are results-oriented. You ask questions such as, how did it turn out? What finally happened? What is the final score? How long did it take? And what's the bottom line? Everyone is always looking at the results. After all, results are the whole point of all the toil and trouble in the first place, right? But how did the results happen? Why did they happen? What specifically caused them to happen? You want to know the answers to these questions because if good things happen, you want to know how to make them happen again. And if bad things happen, you just as surely want to know how to prevent them next time. This focus on the process stems from determinism. Determinism is the principle that you can create a desired outcome by configuring and controlling the inputs in a specific manner. In Six Sigma, you analyze the inputs and the process and then implement the best possible combination to achieve your objective. By doing so, you exercise direct control over your environment instead of allowing your environment to control you. You're deterministic, not reactionary, in your thinking. Many companies and organizations want to improve their performances. They recognize intuitively that their performance results are the outcome of all their business and work processes. These processes are quite literally the way business is done. So, to improve the outcomes, a company has to change the way it does business. It wants to change the processes, the function F in the breakthrough equation from the preceding section, and combine the business inputs in a way that produces a better outcome. It's not a wishful notion and not a trick for getting anyone to work harder. The call to change the way you do business is a legitimate search for a way, and there's always a better way. In this section, you find out how to determine the cause and effect relationships inherent in your system and how to sidestep common cause and effect illusions, and how to sidestep common cause and effect illusions. Seeking cause and effect. To know how you came to the result you have, or to get the result you want, you have to examine your deterministic process. Look behind every result, output, and examine the inputs, the process, and the error that combine to produce it. When you know what causes the outcome, you can begin to position yourself to control the outcome next time, and again in the future. Understanding the root cause-effect relationship is the first step to controlling outcomes. Here's a simple example. The guy gets the girl. The outcome. That's the outcome. How did that outcome happen? Well, as all razor companies would have you know, it's because he has a smooth, sexy face. What caused that? It's the result of his shaving process and choice of ingredients, combining hot water, shaving cream, a mirror, a particular razor, and a steady hand to get a close shave. If anything's wrong with the outcome, if the girl thinks the guy's face is too scruffy despite the shave, you examine the ingredients and shaving process to determine the root cause of the problem. Regardless of complexity, literally every result has one or more causes. The more you can single out these causes and understand them, the better your opportunity to change them for the better. In Six Sigma speak, you'd say that knowing the x's, the function f, and the amount of uncertainty e, means you know what caused the outcome y, cause and effect. Correlation doesn't imply causation, resisting superstitious delusions. Be careful not to confuse coincidence with cause and effect. Just because two events happen together doesn't mean that one caused the other. People often assume that events are closely connected, either spatially or temporally, are somehow also connected causally. These mistaken assumptions are called superstitious delusions. The Latin term is non causa pro causa, which means non-cause for the cause. Superstitious delusions are why a football coach who once won an important game while wearing red socks now wears them for every game. Did the socks cause his team to win, or did the win stem from some other input or inputs? Businesses are just as likely as superstitious coaches to confuse coincidence with causation. Think about the company that ramps up capacity after just a single great month of sales because it believes this sales boost indicates a market expansion. Only later does the company discover that no expansion was forthcoming and that the increased sales were correlated to a different factor. Even if two variables are legitimately correlated, they don't necessarily have a causal relationship. One may fluctuate in relation to the other due solely to chance, or each variable may be strongly affected by one or more other outside or confounding variables that haven't been identified yet. However, a causal connection probably does exist if you can establish all three of the following conditions. A reasonable explanation exists for cause and effect, the connection happens under different environmental conditions, and you've ruled out potential confounding variables. One way to determine these conditions is through a designed experiment where you expose groups strongly similar to one another in terms of the most important variables to different conditions and then analyze them to see whether the variable of interest performs differently. One or more control groups are also held constant and not subjected to treatment or treatments. You can read more about designing experiments in Chapter 18. Principle 2, Reducing Variation. You're playing a great round of golf. Everything's dropping. All you have to do is win the last hole and you're going to beat all your buddies for the first time ever. You step up to the 18th tee, cast an eye down the fairway, draw your club back, uncork your winning swing, and splash right in the drink. You lose. What happened? Variation happened. Error happened. Whatever you did 17 times in a row, you didn't do it the last time. Dang. Consistency is a pain. How do the pros do it? In general, variation is understandable because it creates uncertainty in your ability to produce a desired outcome. Professional results in anything demand consistency. In the world of business and organizational life, the goal is to produce a work product or deliver a service in a predictable manner. That means you get the variation in your inputs, the X's, under control. Some variation within limits may be okay. A little too much variation here or there, and you may have some repairs or rework on your hands. Too much variation altogether, and you're either out of a job or out of business. The characterization, measurement, analysis, and control of variation is a central theme of Six Sigma. Reducing unwanted variation is the key to achieving Six Sigma improvements. To jump right into the statistics of variation, go to Chapter 9. Understanding variation. Very simply, variation is deviation from expectation. If you toss a coin, what's the chance of it landing on heads? 50%. Therefore, if you toss a coin 10 times, your expectation is to get 5 heads and 5 tails. Take out a coin and toss it 10 times. What happened? Did you meet your expectation? Try it again. What happened the second time? Try performing successive sets of 10 coin tosses. Every time you repeat your 10 coin tosses, the output, the number of heads and tails, varies. The extent to which your experience deviates from expectation is the extent to which variation has occurred. When you closely measure any output, y, you find that it varies, always. The point is important to understand. Every output varies. Each time you park your car, it doesn't fit exactly in the same place between the parking lines. Every single product a company makes varies, however minutely, from every other single instance of the same product on every dimension, such as weight, size, durability, and so on. Every time you call a company for help as a customer, you get a different level of service, and you leave the call with a varying degree of satisfaction. The size, trends, nature, causes, effects, and control of variation are the undying obsession of Six Sigma. Nothing is more examined or more addressed in Six Sigma than this principle. The variation of actual occurrence versus the mean is a comparison you make frequently in Six Sigma. If you measure the occurrence of something many times, it's going to vary around some average or mean value. The mean is the central tendency of your process. Flip that coin enough times, and you see that the mean tends toward 50% heads and 50% tails. Anytime you measure the value of a given occurrence or event, it's going to vary from the mean. A player's batting average may be .302 for the season, but Friday night he went 2 for 5 and batted .400, nearly 100 points above his average. And then Saturday he went 0 for 4. That's all thanks to variation. Categorizing common cause versus special cause variation. Variation comes from two sources, common causes and special causes. Some variation is just natural. You can eliminate it. That's common cause variation. The natural forces of nature work to mix things up. It's simply part of the normal course of events. Consider the earlier coin toss example. The variation in the number of heads from set to set is perfectly normal. Or consider the variation in the time between waves at the beach or in the height of trees in a forest. These items are all examples of naturally occurring variation. Now consider a few examples in human systems. Think about the time each day when the mailman comes or how long it takes to process a credit card application. They all vary. The variation is a natural part of their systems. You can act to reduce common cause variation, but you can't eliminate it. It's natural, and it's part of every system. It's in there, and it's not going away. It's embodied in the E of the breakthrough equation. See the earlier section, starting out with one simple equation, y equals f of x plus e. Special cause variation is completely different. It's directly caused by something special. If the mailman usually comes at about 11:30 each day, but gets a flat tire on Tuesday and doesn't come until noon, that's a special cause of variation. If it normally takes 15 minutes to process a credit card application, but the network connection goes down and prolongs the procedure, that's a special cause. These special causes are specific things you can identify and do something about. Special cause variation is captured in the X input factors of the breakthrough equation. With Six Sigma, you spend particular effort to understand the difference between common cause and special cause variation because they're so different and because you go to special effort to identify which type is causing the variation and how it's affecting the outcome. Coping with variation. In general, you should work on reducing special cause variation before trying to reduce common cause variation. When you have special cause variation, the process isn't stable or predictable, and you can't be sure of what is happening. But after you've taken the special cause variation out of a system or process, you can then improve its common cause variability. For example, suppose a coffee house is getting a lot of complaints about inconsistent drink quality. If the coffee house first eliminates the special employee-to-employee differences in making a cup of coffee, it can then effectively work on improving the inherent common cause quality of the coffee itself. But if the initial focus is on fixing the inherent quality of the coffee first, the special employee-to-employee differences, such as the fact that Bob doesn't put the correct amount of coffee grounds in the machine, will cloud the situation, blocking all efforts to determine what's really going on. The goal is to understand variation, control it, and minimize its impact, while accepting that it's part of everyday life and a part of every organization. Just like you can understand and characterize the relationship between the X's and the Y, you can characterize variation and error in the ability to produce desired outcomes consistently over time. This measure of control provides the foundation and framework for implementing real changes in the way you do what you do, changes that have the greatest possibility of yielding positive results. We're adrift, peaking at short-term and long-term variation. Another important characteristic of variation is the way in which it changes over time. Recognizing the difference between short-term variations and long-term variations is important. Here's an example. That mailman used to come at 11:30, give or take a few minutes, but lately he's been coming later and later, and now it seems he's here closer to 12:15, which is really annoying because we're at lunch and he has to leave the packages out in the rain. In this example, the short-term variation of a few minutes was inconsequential and well within the worker's tolerance level. But when the mean time of arrival experienced a long-term variation, perhaps caused by a seasonal shift in weather or the holidays, drifting out by 45 minutes, it became a problem. Chapter 9 covers short and long-term variation in more detail. Principle 3, measuring for success. The principle of measurement is one of the fundamental tenets of Six Sigma. You may boast lots of knowledge about your processes, but until you translate that knowledge into numbers through measurement, you're bound to the world of gut feel, guessing, and marginal improvement. Likewise, you may work very hard and bring significant resources to a performance problem or improvement goal, but without measuring your Y's and X's, your ability to improve will be weak. This idea is nothing new. British scientist Lord Kelvin brought it up in 1891. You can read more about his comments, including the important original quotation in Chapter 9. Taking measurements is a matter of using information and data to quantify the relationship between inputs, outputs, and error in a given system, process, or operational model. Measuring many of your inputs and outputs may seem impossible, but resist the urge to rationalize yourself into believing that some things just aren't measurable. In the long term, achieving your goals without the measurement data that can help you is going to be much more difficult. Minding your Y's and X's. Measurement begins with the output Y's and then extends to the input X's to understand the causes. For example, you'd probably love to have $1,000 in your bank account, the output Y. To measure how you're going to do this, to measure how you are doing on this objective, you can check your account each day and see how much money is there. You'll probably discover that your performance toward this objective is well below what you want. As you analyze the situation, you'll discover that the amount of money in your account is a function of how much money you earn, how much is taken out of your earnings and taxes, and how much you spend on necessities. These factors are the X's. You can't affect the amount of money in your account directly. You have to do something to the identified X's to make Y change. To affect a change in the output Y, you start to measure and control the performance of the causal X's. Perhaps earn more and spend less. Many people never get past the Y. They watch it, like the money in their account, hoping that it will change simply by being measured. Such Y-dominated thinking and measurements is an easy pitfall. Consider the company that continues to work harder and force productivity in an attempt to improve results, the Y, without quantitatively investigating the contributing factors to success, the X's of scrap, excess inventory, poor quality, and so on. This approach has a tendency to self-destruct in its blind push toward a goal. Summing it up with data. Understanding how to measure certain input and output variables is easy because they are, by their very nature, accommodating of such measurement. Examples include the time it takes to complete a certain job, the number of days that transpire between a customer order and the delivery of the product, and so on. These measures are all numerically quantifiable. Such measurement-friendly events, processes, variables, and transactions are well supported by certain measurement tools, such as software, a spreadsheet, a clock, and so on. Using various quantitative scales such as width, length, time, rigidity, and density, you can quantify the behavior of many Y's and X's and their relationships. Other Y's and X's, however, aren't so easy to measure because they're not as easily quantified or because the time, cost, and effort involved in doing so is extreme. How, for example, do you measure customer satisfaction or a customer's opinions? Even when numbers or direct measurements aren't available, you can create them indirectly. In this sense, you take a deterministic approach to measurement. You don't give in to the lack of data. You find the data you need or create estimates in accordance with sound practice. Head to the earlier section, Principle 1, Recognizing Determinism, for details on this Six Sigma principle. In these cases, measurement instruments have to be specifically designed, such as a survey question that ranks responses. With such instruments, you can make otherwise qualitative data much more quantitative in nature. Principle 4. Applying leverage. If you've ever tried to move a huge rock or boulder, or even your washing machine, you can appreciate the meaning of leverage. Although you may lift and pull on the boulder with all your strength, it just won't budge. But if you use a long pole and an object for a fulcrum, you maximize the force of your limited strength. You use leverage to move the rock and accomplish your goal. In Six Sigma terms, leverage is the ability to apply effort toward the critical few X's that have the greatest impact on your desired Y. You have to expend a little effort to find the leverage, but when you do, it catapults you over your problems and through the obstacles that stand between you and your goal. The vast majority of leverage or impact power in creating any desired outcome comes from a surprisingly small number of contributors. This fact is true for the simplest of goals, as well as for the most complex systems. Improving the outcome of all comes down to finding those critical few inputs that give you the leverage. These vital few enable you to move the boulders in your life, your process, or your organization. Appreciating the difference between the critical few and the trivial many. The law of the critical few versus the trivial many comes from the work of early 20th century Italian sociologist and economist Vilfredo Pareto. You may also know this law as the 80-20 rule, where 20% of the inputs in any system account for 80% of the influence on that system. In his dedication to exploring the nature of individual and social action, Pareto determined mathematically that, although many factors are connected to a given outcome, only a few carry the weight to change that outcome in a significant way. In a process, a few key variables are the cause of most performance problems or defects. This principle holds true even when you analyze the impact of dozens upon dozens of variables involved in complicated assemblies and subassemblies with hundreds of separate parts. When you look for leverage in business, you search for the minority of variables that provide the majority of power in solving problems in manufacturing, assembly, distribution, procurement, accounting, finance, customer service, and so on. Although businesses often employ sophisticated statistical tools to find leverage, you may or may not need such tools for finding leverage as individuals. The key is to know with certainty that, whatever your goal or situation, leverage does exist. Some factors in a given situation are more powerful than others. Similar to illusions of cause and effect addressed earlier in this chapter, leverage may not exist where you think it does. The obvious isn't always the correct answer. Look closely, apply tests, and challenge your assumptions to find the true sources of leverage. Note also that the factors that represent leverage in one situation may not represent leverage in another similar situation. Each process or problem has its own unique dynamics and interactions. Pick your critical few battles. You just can't manage all the factors, contingencies, and dynamics when you're trying to break through to new levels of performance and success. Attempting to control every detail is a slippery slope. The trivial many will bury you in a pile of unnecessary cost, trouble, worries, and wasted energy, and valueless action. No one and no company has the luxury or reason to manage all the details. Instead, the right path is to manage only those that are critical to producing the outcomes you desire. Focus on the inputs that really matter and leave the rest alone unless they become significant. After you determine that a factor is insignificant, don't waste time and energy putting attention on it. You'll just spread your energy too thin and minimize your ability to create positive change. The key is to engage in a filtering process by which you weed out the many trivial variables that compete for your time but offer no real advantage. By doing so, you disable the force of confusion and achieve clarity of focus around your efforts to resolve an issue, solve a problem, or reach a goal. Separating and utilizing the critical few. The way you find the critical few is to follow a structured process for defining, measuring, and analyzing all the cause and effect relationships. In Six Sigma, structured and powerful tools help you brainstorm the possible causes, X's, of performance problems and operational issues. The chapters in parts 2, 3, and 4 give you the nitty-gritty on the appropriate processes and tools. Collect performance data that reflect the behavior of the many X's, as well as the behavior of your Y of concern. Analytical tools enlighten you as to which X's are the critical ones and which are the trivial. The results of these operations tell you, and show you objectively and clearly, which X's you need to focus on to impact your Y. They also show you which X's are out of control, or behaving too erratically. Such variation is the primary cause of problems in performance predictability. When you have your baseline of measurements and understanding numerically how your X's interact and impact your Y, you can then implement countermeasures, different X-related actions that ultimately improve your Y. Head to Part 4 for details. Using your same data framework, you can take new measurements to test the impact of your countermeasures. You have established a data-oriented baseline against which to prove that the new way of doing business is truly a better way, and you validated that the critical few X's are truly the critical few. This confirmation is the essence of the Six Sigma principle in finding the leverage. Principle 5, managing risk. In a perfect world, there would be no error. The E in the breakthrough equation earlier in the chapter. The input X's and the transfer function F would completely describe the output Y. In this world, weather forecasts would be exactly right. Financial stock charts would display perfectly smooth and predictable trends, and a card player's selected strategy would fully determine the outcome of the game he was playing. But the world isn't perfect. Every system, scenario, and situation has some amount of uncertainty and risk. Although the f of x term in the breakthrough equation represents exact determinism, the E term captures all this uncertainty or risk. It expresses the fuzziness around which the final answer always varies. We discussed determinism in the earlier section, Principle 1, Recognizing Determinism. You must match risk to the business decision you're making. In some situations, risk, E, must be painstakingly minimized. In making go, non-go decisions for space shuttle launches, the control center painstakingly minimizes uncertainty in its temperature forecasts because a small variation in temperature can create more risk than the system can tolerate. Other situations or decisions can tolerate much more risk. If the mission control director misjudges the temperature as he's picking out his clothes on launch day, the fact that he's overdressed or underdressed isn't going to pose significant risk to the mission. Business processes are exactly the same. Some require very tight risk control, others don't. One of the arts of Six Sigma is knowing how much of the E in the breakthrough equation must be reduced to fit the business decision at hand. Six Sigma gives you the tools needed to quantify risk and know whether you're making an appropriately accurate analysis or have succumbed to the ravages of the all-too-common disease of analysis paralysis. We discuss risk through parts 2, 3, and 4. And that's it for chapter 3.